Hello, this is Garth Wiley from 6DOF Testing and Analysis. Today we're going to talk about durability rig testing and its application to product structural durability validation. And this is based on our experience over the years. And this particular video is really one of a series where we're looking at several different approaches to product structural validation. With regards to the rig durability validation, it really borrows activities and methods from the field testing validation and very often ties in with the proving grounds validation. So we're giving a little bit of an outline of some of our experiences in all of these areas, but this is not a cookie cutter type of validation procedure. There are many variations of it, and these variations can relate to the nature of the product and are adapted to specific situations. And often the validation activities we're involved in have some form of partnering with our customer. Sometimes it takes on the role of some training. Sometimes it takes on the role of getting the maximum use out of the budgets that are available by using our customers' people to help support this process. Generally, our customers handle the product design, the CAD model development and simulation that's involved in evaluating different loads on the structure and so forth. And our role generally is in the validation process. However, sometimes the loads that are really needed at the design phase when the product is being developed are not well known. And if that is the case, there is work that could be done in front of the design process to give us an idea of what the duty cycle environment, what the loading environment is, and particularly looking for what might be large, unusual loads, sometimes with data gathered over a long period of time. So we have some techniques for putting measurement systems on vehicles. They can go out into the field into whatever operating condition they may normally run for. And we can take data for days or even months to completely document the entire duty cycle. And depending on the nature of the testing, sometimes this equipment is highly ruggedized, depending on the environment that the product will be in. As part of the test planning, we use the finite element model to help us locate strain gauges and other instrumentation. So we will apply loads like inertial loads, twist loads, or any other specific loads that may relate to an important operating condition. And although these loads may not be the actual loads that the structure sees in operation, they will in all likelihood show us the hot spots. They will guide us to the best locations to put our strain gauges. Because if our strain gauges are not in the right locations, they don't do us that much good. In addition to strain gauge location, other things can be done to measure loads, for example. Parts can be turned into transducers, and this, of course, depends on the nature of the part and so forth, but they can be instrumented and calibrated to directly output forces. And in addition to strain gauges, we may strain gauge bolts, because all of the connections on the structure are very important. And sometimes we may want to put gauges on a bolt to measure its tension and bending loads as a part of an evaluation of that bolted joint connection. And furthermore, the gauge locations, they often are going to be near welds. And so the welded joint areas are areas that we want to pay particular attention to in making sure that we have stresses in those ranges that are suitable based on welding standard curves and so forth. And then a part of the test planning, we'll also be defining test events. And we need to consider the full range of product configurations and the full range of product weights with payload, without payload, and so forth. And sometimes the without payload condition can be an important condition. The next step in this process involves measuring the field loads and responses. And this is divided down into really two areas. One would be staged events, which we always like to obtain some of these staged events, which could be, for example, a twist load. And we can compare our strains and accelerations and so forth and compare them to the finite element model, particularly where we might have done a twist load in the model. And it just gives us confidence in the model if it seems to be behaving in the same way the structure is. But the real objective of this test is to record typical operation. And this can be running through the duty cycles of the vehicle. These could be, some things could be from a proving grounds, or some of the testing could be done in actual operation. And again, here it's important to get a full range of conditions. In other words, vehicle speeds and different payloads, for example. And so all of this is going to be recorded, and this is going to be used to support our accelerated durability testing. One set of options that should be mentioned here really involves some alternatives we employ for the testing. Often our customers want us to take care of everything, to handle the complete testing out in the field. Sometimes we work in what we call an assisted testing mode, where we actually partner with our customer. We can ship equipment to the customer and to the site, and the technicians can take the data. We would control the measurement system over the internet or cell phone link or whatever, and essentially record all the data without our customer having to know the details of the running the test instrumentation. But it is a way to save a little bit of money, time, or whatever. There are a number of steps that are taken to process the field data that we've just obtained, to process that data so that it can drive the hydraulic accelerated durability test rigs. And sometimes this can be fairly straightforward. Often this can be a very involved process depending on the complexity of the structure, the complexity of the loads, and so forth. But one of the things that we're going to do is to look at the data, and we'll be looking at the recordings while the unit was run in the field and driven through its typical operating conditions. And we're going to find that there are some significant events in there. And there's also a lot of, let's call it dead time, where not much is happening that's significant structurally. So one process we go through is to compress the data by selecting only the significant damaging events. And sometimes this can result in very significant acceleration of the time involved. It can be 100 to 1 or more than that, depending on the nature of the events that are involved in the duty cycle. So once all this is done, we will do some further processing on this data to essentially develop rig drive files. And these will be the files that will actually drive the hydraulic actuators that apply the loads to the structure. And a part of that process is to match key responses of the vehicle. So we want to be sure that responses that we had measured out in the field are matched by the loads that we use to drive the hydraulic rig. In other words, we apply these loads and we make sure that certain key responses are showing the same behavior that we saw out in the field. And one other thing that probably should be mentioned here is nearly always this is dynamic. But there have been times that we've actually done durability rig tests where we're actually putting static loads on based on either measurements we've made or sometimes certain industry standards, and then examining the stresses that result with that and comparing that back to the simulation models that may have been previously used in the design of the structure. And one other thing should be mentioned as well is shake table testing. Now, everything here we're talking about is hydraulic rig testing, either for a complete system or some subsystem or component. But sometimes shake tables are used to essentially apply inertial loads. And an example of this could be a electronic box somewhere on an engine or in a vehicle, and it is subjected to certain G loadings through the typical operation of the vehicle. And so then those G loadings can be applied to a shake table, essentially doing an inertial test of that particular component. How long we actually run the structure on the hydraulic test rig will depend on many factors. The nature of the loadings, the nature of the structure, all will have a big bearing. As the test is being run, we'll be evaluating the stresses, we'll be looking at cumulative damage, and inspecting the unit to see if any failures are occurring. And typically these durability cycles are made up of so many cycles of one type of event plus so many cycles of another type of event and so many cycles of another event. And we look at the cumulative damage that is occurring here. And the objective is to try to compress years worth of life in the field down to a much, much shorter time period. And how much it can be compressed, as we say, depends on many different things. But if we could get 5-10 years of life compressed down into a few weeks of hydraulic rig test time, that would be a good accomplishment. That would be accomplishing the objective that we would like to achieve of really accelerating putting in the fatigue damage into the structure and evaluating how well it will handle from a fatigue standpoint. So essentially, this will end up validating the design for the loads that we have tested. And thank you very much for listening. Any additional information, questions, and so forth, please contact 6DOF Testing and Analysis. This is our website here at 6dtest.com, and we can be reached by email at info@6dtest.com, and our phone number is provided here as well. So once again, thank you for listening.